Hot Jupiters are massive gas giants orbiting so close to their parent stars that their atmospheres are literally being stripped away into space, with surface temperatures exceeding 2,000 degrees Fahrenheit. These bizarre worlds shouldn't exist according to everything we thought we knew about planetary formation. Yet they were among the first exoplanets ever discovered, and they've been challenging our understanding of solar systems ever since. In 1995, astronomers Michel and Didier Queloz made a discovery that would earn them the Nobel Prize in physics and revolutionize astronomy forever. They found 51 Pegasi b, a planet as massive as Jupiter, but orbiting its star in just 4 days, closer than Mercury orbits our sun. The scientific community was stunned. Our models of planetary formation said this was impossible. Gas giants like Jupiter form far from their stars where it's cold enough for ice and gas to accumulate over millions of years. They need to form at greater distances from their stars to sweep up enough material to become massive. Finding one orbiting extremely close to its star violated fundamental assumptions about how solar systems work. But 51 Pegasi b wasn't an anomaly or a fluke. As detection methods improved through better telescopes and more sensitive instruments, astronomers found hot Jupiters everywhere, orbiting roughly 1% of Sun-like stars in our galaxy. These aren't just hot, they're extremely harsh environments that are unprecedented. Take WASP-12b, a planet so close to its star that it completes an orbit every 26 hours. The dayside temperature reaches 4,600 degrees Fahrenheit, hot enough to vaporize iron and most metals. The planet is being stretched into an egg shape by intense tidal forces, and its atmosphere is being blown away at a rate of 6 billion tons per second. Or consider HD 1189733b, which appears deep blue like Earth when viewed through telescopes, but due to its atmospheric composition, the atmosphere contains silicate particles that scatter blue light, and atmospheric winds reach 5,400 miles per hour, 7 times the speed of sound. It literally rains molten glass sideways on this extreme planetary environment. These planets completely rewrote our understanding of planetary migration and solar system dynamics. They didn't form where we find them today. They formed much farther out in cooler regions and then somehow migrated inward through complex gravitational interactions with the protoplanetary disk or with other planets in their systems. Some might have been flung inward by close encounters with sibling planets in complex gravitational interactions. Others slowly spiraled toward their stars through friction with surrounding gas and dust over millions of years. These alien worlds continue to challenge our understanding of planetary science and the physics governing these unusual celestial bodies. The extreme conditions on hot Jupiters create phenomena that seem more like science fiction than reality, yet they're backed by solid observational data from space telescopes like Hubble, Spitzer, and the revolutionary James Webb Space Telescope. Many hot Jupiters are tidally locked to their stars, meaning one side perpetually faces their star in eternal day, while the other remains in permanent darkness and bitter cold. This creates temperature differences of thousands of degrees between hemispheres, driving atmospheric winds of unimaginable ferocity that attempt to redistribute heat around the planet but never quite succeed. On HD 80606b, the temperature swings by 1,500 degrees Fahrenheit in just 6 hours, as its highly elliptical orbit brings it screaming past its star at breakneck speeds. The atmospheric physics at work here is extraordinary and unlike anything in our solar system. These planets have atmospheres made primarily of hydrogen and helium, but at these scorching temperatures, even supposedly stable molecules break apart completely. Water vapor dissociates into hydrogen and oxygen atoms. Methane shatters into carbon and hydrogen. Heavy elements like iron and titanium exist as vapor in the upper atmosphere, creating exotic clouds of metallic compounds never seen on Earth. Some hot Jupiters, like WASP-76b, have iron rain falling from their skies. On the day side, iron vaporizes into the atmosphere and gets carried by winds. Powerful atmospheric currents carry this iron vapor to the night side where it's cool enough to condense back into liquid form, falling as drops of liquid metal through the darkness. Other hot Jupiters show evidence of corundum clouds, essentially clouds made of rubies and sapphires drifting through alien skies. The diversity among hot Jupiters is remarkable and continues to surprise astronomers. Some are inflated to enormous sizes, their atmospheres puffed up by intense stellar radiation until they're less dense than cork and could float in water. Others are compact and incredibly dense. Some orbit stars so closely they're spiraling inward and will eventually be consumed by their parent stars. WASP-18b will crash into its star in less than 1 million years, a cosmic blink of an eye in astronomical terms. The study of hot Jupiters has profound implications beyond just understanding these unusual worlds and their extreme environments. They're teaching us that solar system architectures are far more diverse and dynamic than we ever imagined possible. Our solar system, with its orderly arrangement of rocky planets close to the sun and gas giants farther out, might actually be unusual or even rare. Subscribe to continue exploring these extraordinary worlds and the cutting-edge science revealing their secrets.